All right, good day, everyone. Today's focus is going to be basically dealing with rational functions. We kind of talked about the basics of it last week, going through some certain things about it that causes it to look the way it looks. Okay, dealing with like asymptotes and behavior, why it does the certain things it does. Okay, all those are important ideas that we need to kind of take into account, but then transition those into how are we actually going to deal with transformations. Okay, so here's what I kind of want to think about. Here's what I want you to kind of understand. We talked about this particular graph yesterday. Okay, this is a regular, let me make sure this graph is set up. Perfect. This is a regular rational function type graph, okay, where we have 1 over x. The values are shown on the screen. We have our two asymptotes, both set at 0 currently. And we talked about how basically why this occurs. You know, how I can't plug a 0 in the bottom, which means I can't get the 0 as an answer that comes out. Well, what we want to discuss is how is this actually affecting my problems? Okay, what's actually happening within my solution set? Okay, well, and today with transformations, we're going to talk about all of these over here. Basically, what's happening when I slightly add different numbers to it. So the first one I want to analyze is what happens when we multiply a number on top. Instead of a 1 value, what happens if we have a 2? Okay, this causes our graph to expand outwards, all right? The whole idea is that, once again, if I were to plug a 1 in, it would stretch it up to this 2 mark right here. Okay, and that idea is kind of in place throughout this problem. This is a vertical stretch. Okay, this is going to cause a vertical stretch that presses the graph out. Versus if I multiply by a number on bottom, so for example with the x, this is actually going to cause a compression. Because now when I plug a 1 into this problem, if you really think about that, if I were to plug a 1 in for x, now instead of being at a 2, like this one is up here, now I'm at a 1/2. So notice at 1, I'm at 1/2 sitting right here, okay? That's one of the next ideas I want you to kind of take in and think about. Okay, how is this actually affecting? So a number on top is going to cause a stretch, as in it's going to press the graph out here. While a number underneath is going to compress it, push it towards my 0 function or my asymptotes even more, okay? For the next values, this is where it really starts getting important, okay? Obviously, we've talked about before how the other two transformations are like up, down, left, right, or up, down, and left and right, excuse me. Well, we want to try to understand what's really shifting here. So if this is our original, we have asymptotes at 0, 0. If I do this problem here, notice what actually shifted. Okay, this red line originally that was sitting down here got pressed up. Okay, well, notice how it shifted. Originally, the 0 here, or my x-axis, was my actual asymptote. Okay, so for my original, the x-axis is my asymptote. Well, now what's happening is this graph shifted, but we want to know how it shifted. Well, the line definitely moved, but there was something that's more important that actually shifted with it. This purple line now is restricted based off of x equals 1. Okay, notice how now I can't touch the x-axis, or excuse me, now I can actually cross the x-axis, but my issue is now I can't cross at 1. Both graphs both steady out at that value of 1. So what this actually does is it creates a growth in your actual asymptote. I went from a 0 to a 1, okay? So when I say up 1, how this is a up 1 transformation, it's really not, it's shifting the graph up 1, but more importantly, it's shifting your asymptote from 0 to that 1 position, okay? Now you could probably assume the same thing with a problem like this, okay? Notice how in your original, we have a vertical asymptote that's cut off at 0, so neither of these lines can actually touch at 0. However, when I do a minus 1 at the bottom, which is a right 1 movement, notice what happens. Now the graph shifted, but now I can't cross at that 1 value. So x equals 1 is my new vertical asymptote. Okay, so understand that how we shift the graph is all dependent on how we look at it. Okay, really these transformations aren't necessarily moving the graph, they're moving my asymptotes where I'm actually restricted at, causing the graph to shift with it. Okay, So now when I look at this bottom one, I have a right one, an up one, and a stretch of 2. If I assume kind of how is it going to affect my graph, well, if I look at this, we have an asymptote at y equals 1. We have an asymptote at x equals 1 based off our two transformations. And then thanks to our stretch, now we're pressing farther away from those asymptotes. Okay? So one of the things we want you to think about, one of the things I want you to take into account is how is this actually affecting my graph? How is it actually working this out? Okay? With that being said, that does kind of bring us to the notes. Okay? We want to talk about how can we actually deal with these graphs? Well, in a graph itself, there are certain parameters set. So as you can see on this page here, each of these values or each of these letters cause a specific transformation to happen. Well, going through a couple of them, we have A, which is your vertical stretch. So we have a vertical stretch. We have B value, which is our horizontal compression. And then we have our two values, which is the C and D. The C value causes a horizontal translation. And then we have our D value, which causes a vertical translation. And the main idea I want you to think about with each of those values is how it's actually shifting. The vertical and the horizontal compression and stretch, or excuse me, the vertical stretch and the horizontal compression actually shift that graph either outwards or inwards comparative to your asymptotes. While your C and D, your translations, really what they're doing is they're shifting your asymptotes of where they're originally at to where they're now at. So if I'm going to look at a problem like this, let's just say they want me to graph one of these out. For example, let's say I want to look at number 20. We have a 1 plus x or 1 over x plus 4. Well, automatically, I'm going to look at that problem and say, okay, I have a left 4 transformation. That's the only one I'm dealing with. So if I want to graph this out, I can easily try to assume based off the information what's happening. Well, if it's moving left 4, my vertical asymptote is now at -4. So I can look at this and say, okay, here's my vertical asymptote. My horizontal asymptote hasn't moved, hasn't shifted because I have no up or down transformation. And then automatically I can assume based on how rational functions work that this graph has to be sitting up here and that this value has to be down here. Okay? And that's how we can pretty much assume where my values are at. Okay, those asymptotes are going to guide how your values work. Now, when you start getting stretch and shrinks in there, you do have to start testing points. For example, like 22, you will have to know, like, okay, how are the stretch and shrinks going to really affect it? Okay, and that's an important idea to understand how it's actually going to adjust your problem. But you can just test points at that value. The difference now is how we're actually dealing with these rational functions. And if you're able to move those asymptotes, it's very easy to actually graph it out. Okay? We'll talk about this more in class. We'll go through a couple more problems. Besides that, answer any questions on the Ed puzzle, and I will see you tomorrow in class. Have a great day.